Today we're going to start discussing the machinery or the formalism of second quantization. So we're going to introduce the formalism and introduce integration and annihilation operators, and then we'll solve an example with something called the Schwinger bosons. We'll see exactly what that is, and then we'll talk about one-way operators, which is what you did about an hour ago in the lecture. And for the two-body operators, we're going to have some more lectures first, so we get some concrete examples, because that's where it gets really tricky. Everything we're going to do today can be done in the regular, so the first quantization, we did undergraduate studies, but we're trying to learn the new formalism so that you'll see how it works, and then when you get to more complicated problems, such as two-body operators, which don't exist in first quantization, then you'll be able to use it because you know how to use them. So this is the goal. Note also, and this is an important point, this thing is called second quantization, but there's nothing second. It's not like we quantize once and then we quantize again. That's not the way it works. There's only one quantization, that particle and wave duality. That's the only quantization that exists. And the name second quantization is just a different formalism for the same quantization. Okay, it's just a different name. Don't ask me why it's called that, but don't be confused. There's no additional quantization. Okay, so let's get right into it. Let's consider a quantum system and start with a single particle system. So think about, for example, an infinite potential well. So for the infinite potential well, you have three quantum numbers with some 2 dimensions, which we used to call an x and y and z, and the energies behave like 1 divided by n squared. So that's known stuff. Now, I want to put a particle. Say we have this infinite potential well, right? It's a 3-dimensional box. And now I want to start putting particles into this box. So every time I put a particle into this box, I have to put it into one of the possible states. For example, to state 100, or into state 275, whatever. So I have to choose quantum numbers and put a particle into that state. And we'll assume for the moment that the particles are not interacting. So say I want to put a particle in some state. Say I want to put a particle into state I. So I'm going to put a particle in the state lambda I, which could be, for example, in this notation, state 100. It's one of the possible states that can be populated. So you start off with the vacuum state. So if this is empty, then we denote it just by a 0, which is called the vacuum state. There are no particles. And then I want to populate it, so I use this operator a dagger, and I use this subindex I, which I associate with this energy level, and I apply it onto the vacuum, and then you get a state where the first I minus 1 indices are 0, and then the ith, this is the ith particle, or the ith state. And in the ith state, there is one particle, because I'm putting it into number I. So if I is equal to 1, it's the first one. If I is equal to 10, it's the 10th, right? So that's what this operator does, and that's the creation operator. And of course, you can continue this mechanism. So say you want to put a second particle into the state. I'm going to assume that they're bosons, so that this works. So I'm going to put a second particle into lambda I. So I just apply the same creation operator again onto this state. Again, this is I minus 1 times until the 1. And then you get 2 particles, and there's also a normalization factor, which is square root 2 in this case. and then you get 2 particles in the ith state. As simple as that, right? Yes? Simple, right? That's what I said. Okay, now let's put a particle in a different state. So let's put a particle into a state which I'll call lambda j. And this could be, for example, in the notation of nx and y and z, this could be some other state, say 2, 1, 0, for example. Some other state, just choosing an arbitrary example. And then you have to apply a j dagger onto the state. So the square root 2 here already. Square root 2, 0. And now I get another particle at the jth position. So you have the first I minus 1 particles are empty. Then at the ith position there are 2 particles from before. And then there's some more zeros. And then there is 1 particle at the jth position. So up to here there are j minus 1 particles. For example, j larger than I, not necessarily, of course. So you have 2 particles in the ith level, and 1 particle in the jth level. And this can go on and on and on and on. And that way you can populate and basically write any state that you want by simply starting from empty space. So the box is 0 particles, and just apply these operators and produce any state you want. So at the moment, after doing this 3 times, we now have a state with 3 particles. And the state can now be written as aj dagger, ai dagger squared divided by square root 2 on 0. So what I'm writing here is exactly what we did, but only in 1 step. You first apply, or you start from the right when you apply the operators. So you first apply ai, put hats on them. You start with ai, then you apply ai a second time, divide by square root 2 because of the normalization factor, right? And then I create a particle at j. So this state, which is rather cumbersome to write like this, can be written in a more compact way like this. Basically summarizing what we did, right? Now we can also do the opposite. We can annihilate particles. So we can say, for example, get rid of a particle at A. In state lambda I. So for this I apply the operator AI, on the state to this state, right? That's 0, 0, 2, 0, 0, 1, 0. And then when you annihilate it, this becomes the number 1, because you annihilated it. And you'll get another square root 2 from normalization. And you're back to where we started the step before. So that's a square root 2, zeros, 1, 0. And so on. Now, the importance of the annihilation operator, besides of getting rid of particles, is the fact that you can use it to define the vacuum state. If you now apply say on this state, and you apply some operator AK, where K is different from I and J, you're getting rid of particles, say, the particle over here, the first one, there is a particle there. That results in the number 0. Not the state 0, but the number 0. So in general, if you apply the annihilation operator onto the vacuum state, then you get the number 0. This is the state, the vacuum state, and this is number. And this is true for all I, of course. For all I. So if you know how to write a practical aspect, right? If you know how to write this AI, say, in position space, then you can actually solve a differential equation, right? This times some function equals 0. You solve the equation, and you can actually find the functional form of the vacuum in that basis. But in general, that's not what you do, because we've invented this cool basis called the Fock states, and it is much better and much easier and much more comprehensible than, say, position space, especially if you have multiple variables, then you have an x for each variable. So you have x1, x2, x3. It gets very cumbersome. So you wouldn't do that in general, but just to understand what this equation means, it can be used practically to also find the actual functional form of the vacuum, in case you're interested in it. Okay, questions so far? This is the simple part. It's the machinery. Okay?
It's elements of a Fock.
Yeah, this is called a Fock state.
Okay.
This entire big thing is called a Fock state. With an O, right? Okay, so let's talk first of all about bosons, and then we'll talk about fermions. And then you'll have everything you need. So first of all, let me give you the necessary formulae for bosons. So the general Fock state is what you had in class as well. Square root ni factorial ai dagger hat and I 0. So what this Fock state means is that you have n1 particles in state lambda 1, right? Remember the box? So I have n1 particles inside the state lambda 1 of this box. And then n2 particles in state lambda 2, and so on and so forth. Now, this box has an infinite number of possible energy states. You could plug in n equals 1,000, n equals 1,000,000, n equals 7 million, right? There are an infinite number of states. So this vector, the length of it is infinite, right? So that's why we use all these dots, because there's no way of counting them. Although you could also imagine systems in which there are only a finite number of states, say a finite potential well. If you remember quantum mechanics 1, in finite potential wells you have a finite number of energy levels with E smaller than 0, so there are still bound states, and then it would be finite. But in general, this could be an infinitely long ket, and this is basically a generalization of what we did for this simple case. Question?
Lambda represents the box?
I'm using lambda as it's just a group of quantum numbers. So you can, if it's a one-dimensional system, you have one quantum number. But in a three-dimensional system, you have three quantum numbers. So I'm using lambda as a shorthand notation for all quantum numbers. You can also add spin for, and whatever you want. You can have many quantum numbers.
How do I know if the particles are bosons or fermions?
You're told. You're told whether your system is bosonic or fermionic. You know that. If you don't, make an experiment and try putting two particles in the same place. If you succeed, or you don't. There's another way of knowing whether particles are bosons or fermions, and you know that. You look at their spin. Right? An integer spin is a boson, and a half-integer spin is a fermion. In this case, we're talking about spinless particles, so spin 0. Spin 0 is an integer. That's a boson. But in general, if you ask for practical aspects in your homework, for example, you're told whether it's bosonic or fermionic system. Other questions? Okay, now the next thing you have to know, so this is the definition of the Fock state, right? And then in addition, you need to know what's called the algebra, or the operator algebra. The operator algebra is how the operators behave with each other, and it's basically a bunch of commutators. So what you have to know is that the commutator of A and A dagger for different states is equal to delta ij. So they only commute if they act on different states. If they act on the same state, the commutator is 1. And all the other commutators are 0. So the annihilation with the annihilation operator and the creation with the creation operator, they all commute. This is called the algebra of Fock space, or operator algebra.
זה אחד או מינוס אחד, לא?
Excuse me?
טוב, לא משנה. כאילו זה לא את הדגל לפני ה...
No, so if I write A dagger, then it's delta ij. If I switch the order, then it's a minus. If you don't believe this, then you're going to prove it in your homework. Yay! It's actually a very simple question, because you're given the way that the operators act on the Fock state. All you have to do is apply it, once A dagger, then apply A dagger A and check if it's the same or not. So, quite a simple exercise. Okay, so let's solve a question, an example. Using this algebra. So we're going to consider a bosonic system with 3 energy levels. So lambda can be either equal to lambda 1, or lambda 2, or lambda 3. These are the 3 energy levels. It's a finite system. And now I'm going to put this system in the initial state where n1 is equal to 2, n2 is equal to 0, and n3 is equal to 1. Which from now on I'll just write as 2, 0, 1. I'm not going to write the ends all the time. Just simple order, 1, 2, 3. And we're going to act on this, act on the state with the annihilation operator AI. So this seems like a very harmless exercise. You probably can already guess the answer. If I is equal to 1, then you'll get 1 particle here. If I is equal to 0, then you get the number 0. And if I is equal to 3, then you get this particle. But so we know the solution, and that's not what this exercise is about. I want to show you how we can use this operator algebra in order to also figure out, first of all, normalization constants, and well, I'll show you how to use it basically. And then we'll do it in the fermionic case, where it's a little more complicated because there are minus signs. But we'll get to that. Okay, so first things first, let's start by writing the state as a general Fock state using this formula. So 2, 0, 1 is equal to A1 dagger squared divided by square root 2 times A3 dagger acting on the vacuum state. And I know all of my n's because they're given here, so I just plug the different n's in. It's as simple as it is. And now we need to act on this with the annihilation operator. So what we want to evaluate is we want to find the state, which I'll call psi 1 over square root 2 AI, and then there's an A1 dagger, A1 dagger, A3 dagger, 0. Right? That's what I want to compute. Now, the trick to compute this is what I want to do, the procedure is to take this annihilation operator and I want to move it to here. If I move the annihilation operator from the vacuum, I know what I get 0. But I can't just move it there because I have commutators. So I'm going to use these commutation relations in order to do so. So first of all, I want to switch AI with A1 dagger. So the commutator between AI and A1 dagger, which is AI A1 dagger minus A1 dagger AI is equal to 1. It's equal to delta I1. Only if I is equal to 1, it's equal to 1. So from here you get that what appears here, AI A1 dagger is equal to is equal to delta I1 plus A dagger 1 AI. And of course there are hats everywhere. Feel free to add little hats everywhere. Okay, so we'll plug this in. Now you get two terms, right? So first of all, you get a 1 over square root 2. And then you get a delta I1 A1 dagger A3 dagger 0. And then the second term, you get 1 over square root 2. A1 dagger AI, A1 dagger, A3 dagger 0. So I've succeeded in moving the annihilation operator one to the right. And in the first term, it doesn't even appear anymore, so I'm happy with that. I can easily transform this back into a state that looks like this. And we know what to do with delta, so that's also simple. Okay, so let's do the same trick again. So we can use the same formula once more in here. Touch the other board. And then we'll have to do the same thing again with a 3 dagger. We'll do the same trick 3 times. So repetitive, as you can see. Okay, so we'll do again, right, using the same formula, and we get psi is 1 over square root 2 delta I1 A1 dagger A3 dagger 0. That's just the same thing. And now the second term, I'm going to switch the order, and you get 1 over square root 2 A1 dagger delta I1 A3 dagger 0. And you get 1 over square root 2 A1 dagger AI A3 dagger 0. Okay, that was simple. Now this term and this term are exactly the same. The delta is a number, so you can move it wherever you want. So these are the same terms. So 2 times 1 over square root 2, that's square root 2 in the denominator. That's square root 2 delta I1 A1 dagger A3 dagger 0. It's these 2 terms. And then here, I have 2 more terms when I switch the order here. So you have 1 term which is 1 over square root 2 A1 dagger A1 dagger delta I3 acting on 0 plus 1 over square root 2. And now you get A1 dagger, A1 dagger, A3 dagger, A1 0, AI 0. And that's what we've been waiting for. That was our goal from the very beginning. This is equal to 0. This entire term just falls away. And now you can write down your solution for the different cases of I. You see that psi is equal to, if I is equal to 1, only this term survives. So you get square root 2, 1, 0, 1. If I is equal to 2, then you get 0, the number 0. And if I is equal to 3, then you get this term, which is 1 over square root 2, 2, 0, 0.
Don't you get rid of the 1 over square root 2?
There is square root 2 from the double and the twice A1 dagger, no?
Excuse me?
Each time you do a dagger, you get out.
You're saying this is wrong here?
I don't. No, this is.
That's what you're saying. This is correct and this is correct.
No, A1 dagger applied twice. So 1 you take from 0 to 1,
yeah.
and then 1 to 2.
Yeah, you're right. You're right. You're right. This is definition of 2, 0, 0. Correct. Okay? Simple as that. That's how you apply the algebra, and that's what it's useful for. Now let's do the same trick for fermions. Shouldn't have erased it. It's basically the same thing. So in fermions, the Fock state, the thing about fermions, right, as you know, is that the occupation number is either 0 or 1. So dividing by ni factorial is irrelevant, because 0 factorial and 1 factorial are pretty much the same, right? So the general Fock state is the same formula as before, but I just leave out the normalization because it's irrelevant. It's meaningless. But now the important thing is that the algebra is different. We don't have commutators. We have what's called an anti-commutator. Let me just define the anti-commutator. So for the anti-commutator, I'm going to use curly brackets instead of square brackets. I don't like this notation with the little sag in the bottom. It's really confusing in my opinion. So I'm going to use curly brackets for anti-commutators, and that's better than what most textbooks do, except the one we're using. Most textbooks use this notation. And this is by definition A times B plus B times A. So there's a plus sign instead of a minus sign. And if you just switch all of these square brackets for curly brackets, then the fermionic operators satisfy the exact same anti-commutator relations as the bosons, which is anti-commutators instead of commutators. So it's delta ij if it's A and A dagger, and if they're both of the same type, then they commute to 0. And this is the fermionic algebra for the operators. Okay, so let's solve an example for the fermionic case. So we'll use a fermionic system with 3 states. And in this fermionic system, we put it in the initial state I'm going to put it to 0, 1, 1. That's the state I'm starting it off. And then I want to act onto it with AI. So with the annihilation operator on the ith state. So it looks very harmless, but this time it's not. I'm going to illustrate the difference. We now want to evaluate psi, which is equal to AI hat, acting on A2 dagger, A3 dagger 0. And now the idea is exactly the same. I want to move the annihilation operator to the far right.
How do you know first to operate the A3 and then A2 and not the opposite?
I don't think that makes a difference.
AI
Right, we still because it's the minus sign. That's a good question. How do I know that? It actually does make a difference. Difference in overall minus sign, which is basically the point of this entire exercise. Let's just say that this is what's given. It's an overall minus sign, it's the difference. So it's a global phase in general, so it doesn't really matter.
Can you repeat the last?
He asks, how do I know to use 2 and then 3 and not the other way around?
What's the difference?
A minus sign, because
Why is
of
that?
this. I'll illustrate it as we go along, okay? You'll see why this becomes important. So first thing I want to do is switch this AI with the A2 dagger, right? So now I need to use the anti-commutator. So AI times A2 dagger plus A2 dagger AI is equal to 0, is equal to delta I2, which means that this operator here, AI A2 dagger is equal to delta I2 minus A2 dagger AI. So when I plug this in, we get delta I2 A3 dagger 0. And now we get a minus, and that's what's the new thing about fermions, this tricky thing about fermions. We get a minus A2 dagger AI, A3 dagger 0. Now I'll do the same trick again for the next operator. So for the second term, for AI and A3 dagger. And then we get psi equal to delta I2 A3 dagger 0. And now from the first one I stay with the minus. There's a minus A2 dagger delta I3. And then there's a minus from here, and a second minus from the commutator, from the anti-commutator. So there's a plus A2 dagger A3 dagger AI acting on 0. Right, so every second term is a minus, every second term is a plus. Of course, once again, this is just equal to 0 because of the definition of the vacuum. So even if you made a mistake here, that's fine in this case. But if it's longer, then you have to pay attention. Right. But that's equal to 0, and now you can write down the state. So it's equal to the number 0 if I is equal to 1. It's equal to state 0, 0, 1 if I is equal to 2. And it's equal to minus 0, 1, 0 if I is equal to 3. So you'll see that in the case of the fermions, unlike the bosons, right, if you compare the two, you get these minus signs appearing out of nowhere. And this is all due to the anti-commutation relation. And that's where it comes from. That's why when you have fermions, you have to be extra careful. So do you like fermions? Well, it's a phase. Minus is e to the I pi. It's a phase. So if you just remain in a phase which is in a state which is only 0, 1, 0, then it's a global phase and it's irrelevant. But if it's part of a superposition, then you've changed the phase, the mutual phase of the relative phase of the two states. And that, as you know, is important. Change the interference between two states and so on. Another thing this leads to, I didn't show this explicitly, it's not on the homework either, but another thing that you can show within a few steps is that the commutation, that the anti-commutators, that these anti-commutators, they lead directly to the Pauli exclusion principle. So the fact that a dagger squared on any state is equal to 0 follows directly from the anti-commutators. And you can show that within like 2 lines. So I encourage you to do that if you want to do that. So the fact that we know about the Pauli exclusion principle kind of tells us that we have to use anti-commutators, or the other way around. We impose this as a postulate, and then we get the exclusion principle as a consequence, whatever you know. Potato, colloquially, whatever, however you want. Okay, we'll solve one more problem for the fermionic operators. Just to put this in a little context, because you might be more used to think about operators in terms of matrices. So let's try and figure out how to write a matrix of such an operator. So we're going to consider a 2-level system, a fermionic 2-level system. Two-level system means that lambda can take 2 values, either lambda 1 or lambda 2. It's a 2-level system. And we want to find the matrix representation of a dagger, of A1 dagger. Matrix for A1 dagger. Okay, so how do we write matrices in quantum mechanics? First step. Little squeezes with operators, but we need a basis, right? So we need to choose a vector basis for our states, right? So first of all, we have to identify how many states we have. So there's a 2-level system, but how many states are there? 4, not 2, right? Because it's a many-body physics, right? That's what's new. They can be in state 0, 0, no particles. Can be in state 1, 0, in state 0, 1, or in state 1, 1. So now you see that if I had chosen a 3-particle system, or if I had chosen a bosonic system, then the matrix is infinite. That's why I chose a 2-level system for fermionic particles. And also in your homework you have 2-level interference.
But in the tester it's bosonic.
On the test you'll have a bosonic system, yeah. Okay. So now I have to identify each of them with vectors. So I'll just identify this with E1, so 1, 0, 0, 0. I'll identify this with E2, and this with E3, and this with E4. You know the notations of the right? This means that it's 0, 1, 0, 0, and so on. That's the vector basis I'm choosing, and of course, this is arbitrary. You can choose whatever you want. If you don't know how to do this, then you should go over Quantum Mechanics 1, because, well, I taught half of you, so you should know this. If you don't, then that's your problem. Okay, so now we have to find the matrix elements. So we have to take the sandwich with this operator, and there are actually only 2 that are non-zero, because A1 dagger acts on the first particle. So if it acts on here, that's okay. If it acts on here, you get 0. If it acts here, that's okay. If it acts here, it's 0. So I only care about acting on here or on here. And if I act on this state, then I get this state, right? So sandwiching between this and this state, for example, is also 0. Right? So the only 2 non-zero states are the one I just pointed out, in which case it's equal to 1, and the state where you act with A1 dagger on 0, 1, in which case you get 1, 1, and it's also equal to 1, and then you can fill in your matrix, so you get a lot of zeros and a few ones. 0, 1, 0, 0, and then a bunch of zeros over here, 0, 1, 0, and all of these are zeros. Now you can check that when you apply this matrix and use your fingers and act on this state,
the columns are exactly the A dagger on the basis.
excuse me?
The columns are the operator on the basis. The first column is the operator on the first basis.
What? Come again?
The columns of the matrix is the operator on the basis. It's like the operator acts on the basis. If you act on 0, 0, you get 0, 1, 0, 0. It's like this.
I'm not quite saying, you're saying it's a mistake?
No.
You okay with it? Okay, I don't understand your comment. probably my problem. So this works, right? Right, if you act on E1 with this thing, then you get E2, right? Which is what you're supposed to get. So this works. Okay, cool, simple example. Now let's do Schwinger bosons. Schwinger was a great guy. He has a Nobel Prize in Physics for something really, really complicated called quantum electrodynamics, which is like 3 courses in front of us. But he also did some simple stuff, which is what we're going to do now. He actually got the Nobel Prize together with Feynman, who you've probably heard of, and some Japanese guy called Tomonaga or something. So enough about history. Let's talk about the Schwinger boson model. Okay, so the Schwinger, it's basically a way to talk about a single particle with spin, but in the language of second quantization. Okay? So if you consider a single particle with spin s, spin s. So you can write this in the state Sm, where m is the z coordinate of the spin vector, and you know that the different operators. This will be important in a second. So just reminding you of some operator relations that you should know. And if you don't, then I'm reminding you. So remember that you have Sz, and then you can use Sx and Sy in order to form raising and lowering operators. So to increase the spin by 1 or to decrease it by 1. Decrease the m, not the s. The s stays constant. You increase and decrease the m with s plus and s minus, and then they satisfy these commutators. Now the model, Schwinger's idea says, instead of thinking about one particle with a spin, you should think about 2 particles, 2 bosons, actually 2 types of bosons and 2 s particles. So use a n equals 2s particle system of type A and type B bosons. I'll make a sketch in a second. So the idea is the following. What you know is that you have a particle that can be in state SS, SS minus 1, and so on, until you get to S minus S plus 1 and S minus S. Right? This you know. And you have raising operators and lowering operators. So S plus takes from here to here, and from here to here, that's S plus. And S minus does the opposite, takes you all the way down. Right? That's well known. Now I'm associating this with a different type of system where I have 2 types of bosons, one type I call A and one type I call B. And then Na is the number of A bosons, and Nb is the number of B bosons. And now, the first state.
Like a single particle? No, talking about it.
I was saying, this is the picture that you know, single particle.
Okay.
And now associating each state in the system with a different system in which there are many particles. Okay? The top state, where I'm in SS, in the single particle case, I put 2 S particles in 2 S of type A bosons and 0 type B bosons. Okay? I then put, in the next state, I put 2 S minus 1 A bosons and one B boson. And so on and so forth. In this second last from the bottom, I have one particle here, and then 2s minus 1 here, and then 0 and 2s. That's the association. So you can think of the system in the same way, because you have the same number of states in total, by just associating with each spin state a many particle state. And you see that the number of particles is always 2s in each state, right? Okay, so that's the first step. Now that I'm talking in terms of many particles and bosons, and I have to use the operators that we know, creation and annihilation operators. So I'm going to introduce something I call a dagger, which creates an A particle, an A boson. And A, without a dagger, which annihilates A bosons. And the same thing I do for the B particles. There's a B dagger, which creates them. The B dagger that creates them. Ah. Oh, yeah, you're right. You're right. You're right there. There's a B that destroys them, and a B dagger that creates them. Okay? Now I can go through all the states also in this system.
But you can't do only one of the operators, right?
So now I have to see how we translate the operators. That's what we're going to do in a second. Question?
How do you know that you can do this? You will show now?
What? I haven't done anything yet. I haven't done anything yet. I'm just translating from spin to many-body physics. Here, this is Hebrew and this is English, and I'm translating. I'm using a dictionary. This is your dictionary. How can I define the operators?
How can you tell this is a boson and this is a
Ah, it's a boson because you have two S particles. It can't be a fermion. Right? Do you know of any other thing besides bosons and fermions? They're called anyons. They exist, but never mind. For a different type. Marianas are fermions. You say Mariana? Marianas are fermions. But there's something called an enyon, which is any type. It's an enyon. But that's for a different type. You're seeing something interesting when you go to more interesting courses. There's one thing we have to do, though, so that this works, and that is we have to define commutation relations. Since they're bosons, you have to use the commutator. So they're equal to 1, and all the others are equal to 0. So that's nothing has changed. Okay. So let's go to the problem. So we would like to solve. First of all, we would like to write S plus and S minus in the language of A and B. And also as Z.
What's the commutation relation between the A operators and B operators? 0?
0.
Okay.
It's like AI and B and AJ, right? So the fact that I could call them A1 and A2.
Yeah. Okay.
And in B, we want to prove these commutation relations with by using these relations. So if I call this equation 1 and this equation 2, then I want to prove 1 using 2. So you see, let's start with A. So I want to write an expression for S plus. So So what does S plus do? It takes me from here to here. So what does that mean in this language? You see right away. I have to use both A dagger and B. Right? So if S plus is equal to A dagger B, I'm doing exactly the same thing. And S minus in that sense is A B dagger. And you can note that these are the Hermitian conjugate of each other, which has to be that way, right? That's cool. It's already working, right? I haven't even tried it. Yes.
Okay, so you stop at the edges because you have.
Yeah. So you have to, but that happens automatically because,
Yes,
right?
you also destroy.
You destroy it.
Do you need to normalize? Like
S plus and S minus? No, they're okay as they are.
S plus is really equal to A dagger times B, is square root of something.
I've absorbed it into the definition of the operator. A takes me directly to 2s minus 1 without constants. I can absorb that into the definition of the operator. There's nothing.
הנוטציות שם זה ספין הכולל, נכון? כאילו, שני S.
Here, 2s is this s.
כן.
Right? So if s is equal to 1 half, this is equal to 2s is equal to 2. It's equal to 1. Right?
But if you do define these operators with a normalization, then is A dagger A still the number operator?
A dagger A is still the number operator, yes. And you will actually show that in your homework.
רגע, אוי, זה לא
Okay, SZ. And this was a question?
אוקיי.
SZ. Remember what SZ does? It takes out, in this case it's easy, right? It takes out the M. So how do I write SZ in terms of A's and B's?
The operator of the sum and the minus of NA and NB.
Right. NA minus NB divided by 2. Right? You see that? Take NA minus NB divided by 2 and you're there. So we do 1 half of A dagger A minus B dagger B. Now you have a Z.
Why not A dagger A minus S?
A dagger A minus S. That won't work. Will that work? I don't think that'll work. What, S is a constant?
That's S is total spin. S.
Yeah, that's not going to work.
Why?
Well, it'll work in this case, but what's going to happen over here? You're going to get minus S. Ah, that will work. Interesting.
But you don't have
לא,
S.
באחד...
You need to write S with the A dagger B and show this is the same or different.
What?
So maybe it does work. That's interesting.
It could work, but you don't have S.
No, you're right. It looks like it does work. It looks like it works.
Let's go.
So you can do the exercise with your operator as well and prove that it works, okay? Because now what we have to ultimately do, in order to show this actually works, we have to show that these operators obey these commutation relations with this algebra, right? If that works, then this algebra is correct. If not, then the algebra is not correct. So maybe that's where you're, because you have no B's, then how will you ever be able to? Maybe it'll work. We'll have to try it. I encourage you to try it.
Maybe you would like this with some.
And then we can call it the Schlinge-Offic boson. Could be worth it. Okay, so let's start. Let's do the commutator between S plus and S minus. There are many ways of doing this. You can either start opening up commutators, or you can use the chain rules for commutators. There are a lot of ways of doing it. What I'm going to do is just plug in the definition of S plus and S minus. So this is B. And then I'm going to open up the brackets. So I get A dagger B, A B dagger, and then minus A B dagger, A dagger B. Then, because A and B commute, I can just switch their order. So I can write this as A dagger A, B, B dagger, minus A dagger, B dagger, B. And now I'm going to switch the order by using the commutators. So I'm going to switch here. I'm going to do this is 1 plus B dagger B. And this is 1 plus A dagger A. Now the term with A dagger times B dagger B is the same as A dagger A times B dagger B. There's a minus sign, so this cancels with this, right? See that? And what's left is A dagger A times 1 minus B dagger B. Now look at your SZ, it's twice SZ, and that's what we wanted to prove. Okay? I can do the same for SZ with S plus. So that's 1/2 A dagger A dagger B, minus B dagger B, A dagger B. Right, I already took the commutator apart with this minus sign. Now, I won't do the entire thing, but I'll just tell you what you have to do. There's a little bit of algebra involved in this, but you sure remember that way back you proved this really neat and very beautiful property of the commutator. It's not the Jacobi identity, it's just opening commutators. There you go. As simple as that. This is on Wikipedia. But actually Wikipedia has different. Wikipedia inverses these two and these two. And you can show it that it's the same. If you invert both of them, both D and B and A and C.
Why can you invert them?
Do it. Right above them, open the brackets. Prove it.
Okay.
There's no deeper, not that I know of, deeper physical meaning to why it's the same. It's just, you know, open it all up. So when you do all of this, and then you get get 4 commutators here and 4 commutators here, so a total of 8 commutators, and then you use the Schwinger algebra, this thing here, use these equations, and then you'll see that 2 of them are actually these, which are 1, and all the other commutators will be 0. And then you end up with only 2 terms, and of course it'll work out exactly, and you'll get what you have to get. So making a long calculation short, you'll get A dagger B, which is S plus. And if you do with this minus, then you'll get what you have to get. So I encourage you to go over this together with a cup of coffee, or maybe like a big cup of coffee because you have some algebra to do. It's not more complicated than what you did in your undergraduate studies. So the main point of this exercise is first is taking this in, right? Understanding how you can do. You can always do this. You have to be smart enough to invent a system that works. But say you have a system, and this one works, then understand how you can translate from one system to the other, from one language to the other, because you're trying the same physics. What you think is a spin of a single particle that can take many possible values, or in terms of 2 different particles, but the particle itself has no internal structure, right? There's no energy levels of A and energy levels of B. It's just either there is an A, or there's 2 A's, but the A itself is always the same energy or the same value. There's no difference, right? So you translate into a different language, and this is what it's all about. So this is what I want you to take home. That's the take-home message, and you also have an exercise, a C, after this to actually show how to use the vacuum state, the Schrödinger-Rosen vacuum, for the state as well. So basically, you'll see how to create all these states out of the vacuum.
Why are they helpful, these states? Why not just stay with the usual...
Well, you can, but we're trying to learn something new. So I could teach you this again if you want,
No.
but I prefer teaching something new.
No, why did Schwinger...
Why should you think of it? I have no idea.
Okay.
What happens in the mind of a genius is beyond me.
Really, is it?
Come on. Come on. Don't give up on that. Okay, last topic for today. One-body operators. So starting again from the single particle systems, which is the well-known thing. You have some operator, which I'm going to call f, and this f acts on eigenstates lambda. So when this f hat acts on eigenstate lambda, you get the eigenvalue f lambda times the state. That's well known. And you have eigenstates and eigenvalues. Now when you want to translate this into many-body physics, so into a many-particle system, then your f, we now add a subindex j because it acts on the jth particle. And when so it acts on jth particle of the Fock state. And then if you want to act with, so you want to act with this state, with this operator on every state in the Fock state, then you have to simply take the sum over all the little f's. And there's a convention that for single particle systems, or for single particle operators, we use little letters, and then for the second quantized many-body particle systems, which is a one-body operator, because it only acts on one body at a time, we use big letters. Now, this thing is called a one-body operator. And this thing is called a single body or single particle operator. And there's a difference between single particle and one particle. Okay? Because physicists are stupid and don't know how to speak English. So single particle operators are particles that act on systems with one particle. And a one-body operator is an operator that acts on a many-body system, but at one body at a time. So when you see this language, just don't get confused. Because then you have to, because a one-body operator is the sum of single particle operators. Right? Okay, now if you're working in the eigenbases of f, so you're working in this in a Fock state where n1 is the number of particles in lambda 1. So you're using the same basis as you would use in the single particle system. Then the operator takes a very simple form. You just have to multiply the eigenvalue by the number of particles in the state. I'm kind of repeating what you saw just a minute ago, and we'll go to an example in a second. So you would write it as the sum over I f lambda I, so it's the ith eigenvalue times ni, which is the number operator of the ith state. Now what if you're working a basis where you're not diagonal? So if, for example, you want to work in the same position space, where, for this sake, f is not diagonal. Then you have to use the more complicated version where you integrate over all the space. So you go to every point in space and then use this operator. Now f of r is just the transformation of this f lambda into the position basis. And this annihilates a particle at position r, then you use the operator, and then you put the particle back. And you'll see why this makes sense when we solve an example. Before we get there, let's talk about the Hamiltonian, the most important operator in quantum mechanics. So the single particle Hamiltonian is just p squared over 2m plus v of r, where r can also be a vector, and so can p, if it's a three-dimensional system. Now, because we want to move this into a many-body physics many-body physics system, we're going to rename this capital H by a little h, so we don't get confused. Now, little h is a single particle operator inside a many-body system. And now the overall Hamiltonian, so the Hamiltonian of the many-body system, will now be equal to the integral d3r, the integral over all space. And you use exactly this formula. So you have a psi dagger at position r. And then you have the single particle Hamiltonian, p squared over 2m plus v of r. And then you use the annihilation operator. These are vectors. So this is the Hamiltonian in a many-body system in position basis. Of course, you can now go ahead and Fourier transform and do whatever you want, go crazy, and if you find the eigenbases, then you can always transform this into a much more convenient form. And your goal will always be to do this. So when you're told to diagonalize the Hamiltonian, it'll typically look like this. So say it's a non-interacting system. So you look at the single particle system, you write on your Hamiltonian, it's your three-dimensional infinite box, right? Infinite well. So you look at that box, and you look at it for a single particle, put it into here, and then you have to find the correct transformation between psi and A to bring to this form. And when you do that, whatever is before the i's, that's the energy of the state with so many particles. So this is what you have to do basically all the time. That's what's called, this step from here to here, it's what we call to diagonalize the Hamiltonian.
Why h is not the sum of the small h? Or is it?
It is a sum, it's an integral. Integral is a sum.
Okay.
But space is continuous.
But why you inserted because you took the momentum and you take him to why?
What did I do?
Why the capital H is not the sum of the small h?
It is.
It is.
Oh, you mean why are the size here?
Yes.
Well, because I need an operator. We always had them. We had them here as well. And also here we have operators. They were here. This is A dagger A.
Okay.
We always had them. We never had something else. Right?
Why?
Is already operator.
Hmm?
The
They are, but they're single particle operators. So this only acts on one particle.
okay.
right? And then you need to go, so this, basically what you're doing, you're summing over all of R. So the first thing that acts, this is an important question, right? The first thing, you have here a wave function. So the first thing that acts in the wave function is this annihilation operator. So this annihilation operator goes everywhere in space and tries to annihilate particles. Now if there's no particle there, what do you get?
Zero.
It's zero. So nothing will happen. You won't get anything to the energy, right? But if there is a particle, then this will stop, annihilate the particle, then you do the single particle Hamiltonian, as if that particle only existed, and then put the particle back. And you do that over all of space, because you're integrating over the entire volume. This sounds a little complicated, but we'll now do an example. We'll now solve an example with a simpler system, with spins, spin 1/2, and you'll see how this makes perfect sense. And if you still don't believe me, then of course there's a homework for this. And in the end, you're all going to believe that it works. If you still don't, I can give you more homework. So whatever you prefer. Okay, so we have 15 minutes, and this is the last example for today. So
What's the epsilon lambda? The sum?
it's the energy states of the ith eigenstate, right? Because then if you have one particle in state I, then you take the energy of that state. If you have two particles, you multiply it units. So
זה הרוב, נכון? כאילו זה הצפיפות, הפסאי.
no, the density is psi dagger times psi.
נכון. אז כשהיא עשתה את פעם קודמת, כאילו סליחה בהרצאה, אז היא עשתה שיש לי רו אופרטור כפול איזשהו ערך תצפית.
So basically, what you're saying, you want to move this to here. Right?
זהו, בעיקרון, כן.
So that only works if this commutes with this.
זהו.
Or it doesn't work.
מהרצאה היא לא עשתה את זה עם אופרטור ביניהם, כאילו היא לא עשתה...
Well, actually, she did it, especially in the two-body case, you saw she did it all the time. There were two operators on the left and two on the right.
נכון.
And always annihilation on the right and creation on the left.
נכון.
Right?
היא עשתה את זה כשרציתי לקבל את הפוטנציאל, למשל, עם פונקציה שהיא סקאלה, כאילו פונקציה שהיא לא אופרטור, היא... אתה מבין מה אני מתכוונת? כי אם יש לי אופרטור לפני, אז הוא יכול כאילו... אני כאילו מפעילה אופרטור על אופרטור.
Let's try and fix the question. What are you asking? Are you asking why is there why other sides on different sides?
אז היא העבירה את זה, היא יכלה כאילו להזיז את הפונקציה, את האופרטור, כי הוא היה סקלר, לא פעל עליו שום אופרטור. אין טוב, אני אשאל לך אחר כך.
Let's just say one word. You can speak to me afterwards, of course, I'd love to, but just going to say one word. In this case, if you're working in position space, for example, you know that the P operator is a derivative over R, right? Or it's a Laplacian, whatever. So you can't just switch it with this because it's a function of R. So here the order matters, right? But if this is just a scalar function, if you had only V of R here, then it doesn't matter. Then you can move it around. But because there's a P here, you cannot do that. So this is the correct way to write it.
Can you please give an example of how you actually take this operator and apply it to A? No more questions.
רק שאלה אחת. פסאי זה של פונקציה של חלקיק בודד או של כל המערכת שלנו?
This side?
כן.
It's not a wave function. It's an operator. You see the little hat? It's an operator. It annihilates a particle at position R. Right? What are the eigenstates of the position operator? Uh-oh. What are the eigenstates of the position operator? A delta function, right? So this goes to position R and annihilates a particle in the eigenstate that it's at exactly position R, right? And this creates a particle at position R, which is the eigenstate of the position operator. Okay? The same way that all the A lambdas did beforehand. Okay, we use psi, but it's not a wave function. That's why I put this little, maybe you didn't notice, that's supposed to symbol that it's an operator. It's something I invented for myself, never mind. Yes?
כשהיא זיזה את זה, היא אמרה, כאילו, בהתחלה זה היה בצד אחד, ואז היא אמרה, בשביל נורמל אורדר אנחנו נזיז את זה לפה, אבל זה גם יש לזה חשיבות.
This is the right way to do it, and to actually get it from... Yeah, okay, I think we've talked enough about this problem. This is the right way to do it. And you'll see in a second in an example why this makes perfect sense. So let's talk about a system with n spin 1/2 particles. So we have n spin 1/2 particles. They're obviously fermions, because otherwise there wouldn't be spin 1/2 particles, right? So if you look at the single particle system, then the operators, there is a little s, which is a little hard to write, a little big s. There's a little s, which is a single particle operator, which is h bar over 2 times sigma I, and the sigma I are the Pauli matrices, and I'll remind you what they are. 1, 1, and sigma 2 is 0, there's a minus somewhere, minus I, 0, and sigma 3 is sigma z, so it's 1 minus 1. And the single particle spin operator is applying Pauli matrix on the single particle state, either up or down, and multiplying by h bar over 2. Right? So there's nothing new here. We always start from the familiar stuff, and now comes the cool stuff. So now we move into the n particle system, and let's write the operator sz for the many particle system. So this is not going to be a big S, capital S. I'm going to now sum over all the little s's, right? And put operators to the left and to the right. So this is h bar over 2. And now we're going to have to sum over the operators. And I'm going to use the matrices. So I have to sum over 2 indices, alpha and alpha prime. Write it first. It's going to be confusing. Write it. I'll explain, okay? You know it's confusing? Keep your hands down. Okay. So it's alpha, alpha prime, then creation operator alpha prime, and then a sigma z with indices alpha, alpha prime. They're the matrix indices. And then a annihilation operator at alpha. It's easier to do alpha prime alpha, because this alpha goes with this alpha. Now, what are these alphas? So the alpha and alpha prime indices, they're either 1 or 2, or they're either up or down. So sigma z is this matrix. So sigma z11 is this matrix element, right? And sigma z12 is 0, it's this matrix element, right? A alpha for alpha equals 1 is a annihilation operator for the down state.
Can you repeat this, please?
So A1, which is equal to A up, right? This is annihilation of up. Annihilation of up spin. And in the same way, A1 dagger, which is a up dagger, is the creation of an up spin. The same thing for alpha equals 2. So many questions, I haven't said anything yet. Yes, go ahead.
Alpha is sum over all the n? Over all n? Or
No, over 1 and 2, here. I've defined it. Yes?
A question regarding the sum. What you do is a little bit similar to what you did before. You had the psi r, it goes over all the r space. But then I didn't understand then and now too. When you annihilate a particle at the r state or a spin now, the sigma is operating over the state of no spin or no particle.
No, I haven't defined a state yet. Let's define a state and act with it.
Okay, always.
Okay, that's next step. It looks confusing, but you'll see it works. And that's what we're going to do in the next few minutes. if you let me. So we're going to consider a state, well, they're fermions, right? So we can have maximum one particle per state, right? So we're going to look at a state where we have one up particle, yes, that's it, one up particle, and 0 down particles. So that's state, what I call 1, 0 in shorthand notation. This is what it means. Up, down means 1 and 2, right? Whatever you want, it doesn't matter. It's just notation. And now I want to apply this big SZ onto the state 1, 0, using the formalism of second quantization. Of course, we all know what's going to happen. Right? There's one particle in the up state, so you're going to get h bar over 2, right? So let's see that this notation actually works. Okay? So again, the goal is not the solution, the goal is the formalism. Okay, so let's plug it in. Exactly what we have to do. So we have to act with it. So we have h bar over 2, sum over both alphas, and then we have an a dagger alpha prime, and then there's a sigma z alpha prime alpha, and then there's an a alpha 1, 0. Now let's start with the first operator acting on the state. So with a alpha. Remember, this is a sum, so there are two terms with alpha. Either alpha equals 1, or alpha equals up, or alpha equals down. So obviously, a up acting on 1, 0, what do you get?
Which one is which?
0, 0.
It's 0, 0, right? The state 0. Not the number 0, it's the vacuum state. It's a state with 0 particles. And what happens for alpha equals 2, so for a down acting on 1, 0?
0.
You get the number 0, right? So out of the two terms, we only actually need one of them. Right? Alpha is equal to 1, in which case you get something, or alpha is equal to 0, in which case you get nothing. Okay, so let's write down what we've done so far. So we have SZ acting on 1, 0 is equal to, there's h bar over 2, sum over alpha prime, we've already summed over alpha. There's an alpha prime dagger. Then there's a sigma z alpha prime, but alpha is equal to 1. So we have to use 1 here. And then we said that when alpha up acts on 1, 0, we get the state 0, 0.
Which one of the indices is the column and which one is the row?
I think the first is the row and the second is the column. But that's something which is really confusing, and you know, whatever makes sense in the end is what is correct. But I think the first is the row and the second the column. If you find a cool way of remembering that, or whatever the correct thing is, then let me know. And the rest of the world, because I don't think anybody understands that properly. It's like in math, we always try one or the other, whichever works is the right one, right? You never actually know before trying. Okay, so is this step clear?
Yes.
Right, I just checked what the alphas can do and plugged in whatever I have. So for now, I've changed the state. Although sigma z is not supposed to change the state, right? But we're not done yet, there's another operator here. So now we have to sum over alpha prime. Now when we sum over alpha prime, so let's say that, what do we say, the second is the column we said?
It doesn't matter, anyway,
Yeah.
we'll get a minus.
Well, yeah, in this case it doesn't matter, but we just stay consistent. So we said one was the,
The first is the row and the second is the column.
okay, so we're in column 1, so we're here, right? This is alpha equals 1. And then we have this one on the top is alpha prime equals 1, and on the bottom is alpha prime equals 2, right? So again, you see, when we sum over alpha prime, only the one with alpha prime equals 1 will contribute, and the one with alpha prime equals, sorry, other way around, only alpha prime equals 1 will contribute, and alpha prime equals 2 will give you 0. Okay, so let's write that down. So we get S Z acting on 1, 0, that is equal to h bar over 2. We're not doing the sum over alpha, so we get alpha dagger, or alpha prime must be equal to 1. Otherwise, there's no contribution. Right? So this is up. You see where I'm going with this? And now sigma z of alpha prime equals 1 is 1, so that's 1. And then there's 0, 0. Now we apply this operator onto here, and this is exactly what you were supposed to expect. Right? So it works. So here you see again how this operator works.
But here
you see again how the operator works, right? First, this first operator, it went and checked in all the states. It went to the up state and asked the up state, are there any particles? Yes, okay, so I'll annihilate you and we'll think about you later. Then he went to the down state. He said, are there any particles in down? No, okay, so I'll put a 0 there. So we can forget about it. Then the middle part, put in the number, the eigenvalue, which is, well, it's h bar over 2 because the prefactor, but you put it in 1, right? It's the eigenvalue. It put it in, and it knew which one to put in because of the alpha. And then it already told you, because you know the operator, it already told you which particles to put back. Now, if this were not sigma z, but say sigma y, then you would get a different particle back. But you know that sigma y splits the spin, right? It's s plus plus s minus, or plus minus s minus. So it flips the spin, right? So that's what this sy would have done. And that's what you're going to do either tonight or tomorrow or whenever you get down to it. But that's what's
So why do you call it many-body?
No, it's a many-body system. Well, my example only had one particle, but I could use more. Two more things to say before you go out. But these are one-body operators, so it acts at one body at a time. That's the easy part. Starting from next week, we're doing two-body operators, which are interactions. But you have to understand this notation, or it's easier to understand two-body systems and two particle interactions if you understand how one body.
But here is not n spin half. This is only 2 here, no? It's the operator.
So my example only had one particle. But so what question is this? And this is actually my next point. What if I want to write this operator? You see that it's a spin 1/2 particle system, so I can only have two particles, right? Those are fermions. One up, one down, then I'm full. What if I have a system, though, where I have more quantum numbers? Right? In order to put more fermions in, I need more quantum numbers. So I can have different spins at different positions, or different momentums, or different, whatever. So in this case, you can also write this operator, but you have to add explicit notation of these other operators. So I'll call these other quantum numbers lambda, and then you basically have the same thing, but now you have to create a particle at lambda alpha prime, use the operator sigma z, which depends only on alpha and alpha prime, and then here you have the annihilation operator of lambda alpha. So you're detecting, with this operator, you're detecting particles in state lambda alpha, where lambda could be, for example, the position or momentum of the particle, and this way you can also have more than two particles in the system. But as you notice that this lambda here it's not in the matrix, and it just gets taken away here and put back here. So these other quantum numbers are just spectators. They don't do anything. But you have to take it away, do something, and put it back. And what's actually doing the actual physics, what's actually doing the actual operator, are the alphas. So it's exactly the same as above, just using more particles. So it's basically the same thing. And in general, and this is where we end, in general, for not just sigma z, but if you want to use sigma I, then basically it's the same thing as for an I instead of a z. It's exactly the same thing. So h bar over 2, sum lambda, sum alpha, alpha prime, a dagger lambda, alpha prime, sigma I, right? I use the I, Pauli matrix, x, y, or z, whichever you're asked to do, alpha prime alpha, a lambda alpha hat. And there we go. So this is the general case for the spin operator.
Okay.
Questions? Yes?
In this formula, you have the matrix element, sigma alpha prime alpha. But in position, when you show the Hamiltonian in position space, then you have the real operators.
Yeah, because R, you have an R in the operator. It's continuous here. So you could write a matrix, but it's infinitely sized. In this way, it's easy to use the matrices because all the matrices exact.
But that's a scalar, and these were operators.
No, it's also an operator. It's multiplication by a number. It's the same thing. It's just easier to think of operators in terms of matrices, right? Obviously, here I also chose a basis, right? I have to choose that up is 1, 0, right? And down is 0, 1. I have to choose that, otherwise this would work.
Of course.
Pauli matrices assume these places.
Of course.
But this is not necessary. That's just it's not equal to this. It's, right, associated.